So from the concept of distributed load, okay, so we can define the resultant force here, and we get we call it as first moment of area my with the respect of y-axis, okay, x bar dA, and then first moment of area in the respect of x-axis dA. So we can use this concept to define our present topic, which is centroid of gravity. Same concept as this one, okay. Our world have a gravitational force, right? Okay, let's say this is your body, okay. So your body is made up of small particle here, okay. So each of the particle is exerted with a gravitational force to become one distributed force in your body, okay. So this distributed force we can represent it as one single gravitational force, which is G, and then the location of the G is in the center of the body, of your body, okay. This center we can define it as x bar and y bar, okay. Or simply we can say we can use the concept of first moment of area, the one we just said before, okay. So this is a simple two-dimensional example. Let's say this is our FR here at the center of the system here. Our FR here is equals to 4 Newton, okay, and then x bar we take from, let's say, from point A, x bar from here to the location of F resultant here, x bar is equals to 3 meter, okay. So your resultant moment is equals to x bar multiplied with FR, isn't it? This is equal to 3 times 4 is 3 times 4 is equals to 12 Newton meter, okay. So if we calculate the summation of moment for the system, which is summation of m about point A here, ma is equals to you have only one. If you neglected the F resultant here, let's say we don't know the F resultant here, so we only have the force from the weight of B here, WB is equals to 3, okay. So this is your only force, which is B is equal to 3 Newton, and then the line of action is from A to B is 3 plus 1, 4, okay. So time 4 meter. This one is also 12 Newton meter, which means that the summation of moment is equals to the summation of moment resultant, okay, which means that any force here that creating the moment, the summation of that we can represent it as one single resultant force of moment, okay. So that's the concept of to explain this the gravitational force, okay, which act at the center of the body. If you do at point B, also same. let's say we take point B. Okay, the resultant moment is equals to 4. The resultant force is 4. The line of action is 1 times 1 is equals to 4. And then the resultant moment for B at point B, about point B, we only have the force for the wake of A here, which is equals to 1. So this is equal to 1. And then line of action is 1 plus 3 is 4. So this one is also equals to 4. Okay, so this one is same with the previous one. Another one important thing is, if we take the center here is as our point of moment, or we call it as summation of M about point G, the sum of the moment will be equal to 0. Let's say we set counterclockwise is positive, one is equals to about point G here. If we take the weight of A going that way, it is counterclockwise, same direction, so it is positive. So line of action is 3 times 1. Okay, 3 times 1. And then at B here, the weight is 3 going that way, opposite with the counterclockwise, which is clockwise, so this one is negative. And then the force is 3, the weight is 3, and the line of action is 1. Okay, so 3 minus 3 equal to 0. So about the point, the center point of G here, the sum of moment will be equal to 0. Okay, take note for that. Okay, so let's go back to this one. Okay, just now I said that we can use the concept of first moment of area to define the location of center of gravity. Okay, so let's say this one. So to use this for center of gravity, so summation of moment about y-axis and x-axis. So this one is defined as a x dA. So for center of gravity, we can change this into weight of gravity. Weight, okay. So this one is equals to summation of x bar d omega, d weight, okay. And then this one also for y bar, we can change it. We can change the area into weight. This one is equals to y bar weight. Okay. So the x bar and the y bar is actually the location of the center of the gravity, which is equals to x bar d omega d weight over this one lah. Okay. This one is when moved to the right side, and then we do also the integration, so the w will become differential of weight. Okay, the differential of weight here, if you want to change into the terms of differential of area, you can use this equation. The differential of weight is equals to weight over volume multiply with volume. Okay, so the volume here, we take if we have an object like this, it has a thickness. Okay, so this is an area, so this is the thickness T. So volume here is equals to area multiply with the thickness. Okay, so because the area is a changing of area, so we can put it as a differential area dt. So this one we can represent it as gamma. So this become the differential of weight is equals to gamma thickness times differential of area. So this is how you want to represent the diffusion of weight into the terms of diffusion of area. So one more thing, if your object is in 3D and then you want to find the location of the center of the gravity, so you will have also the coordinate for axis z, okay, z bar. So this same thing is equals to integration of z bar dy over dy. Okay, so you will gonna have three coordinate, which is x bar, y bar, z bar, to define the location of center of the center of gravity of the object of the body. Okay, so there are some simple geometry object that you can find the center of gravity easily. Let's say like triangle. Okay, so the resultant force or the resultant force of the amount of gravity is simply the area. It's equal to the area of rectangle. Let's say this is the width is b, the length is h. So simply b h is the area, and then the center is simply at the center of the object, which is the x bar is equals to half of the h, okay, and the y bar is half of the b. Okay, this is for simple example. Other example of simple geometry like triangle. So you will have the location of the center of the gravity at y-axis will be quarter of the length b here. Okay, sorry, not quarter, one third of the b here. Okay, this is for y bar. Okay, so there are a lot more of other simple geometry like quarter circular, semicircular, okay, quarter elliptical. So all the simple geometry already have their formula for to find the center of the location of center of gravity, which is x bar and y bar. This for two-dimensional cases lah. Okay, so please check in your textbook for this one. Just for the case if your shape is not symmetry or not a simple geometry, so you need there's a step you need to do to determine the area and then the centroid of the gravity of that particular object. Okay, so this is particularly for two-dimensional cases. So the first one, you need to choose appropriate differential element dA at general point xy. Okay, so generally if y is easily expressed in terms of x, for example y equal to x squared plus 1, use a vertical rectangular element. If the converse is true, then use a horizontal rectangular element. So if you use the function of y, so use the vertical rectangular element. Okay, please remember that. If you use x, then use the horizontal rectangular element. Sorry. Okay, and then the second one is express dA in terms of the differentiating element dx or dy. Then determine x bar, y bar of the centroid of the rectangular element in terms of general point xy. The next step is to express all the variable and integral limits in the formula using either x or y depending on whether the differential element is in terms of dx or dy respectively, and integrate. Similar steps are used for determining centroid of gravity and center of mass. This step will become clearer by doing a few examples. So we are going to apply all the 4 steps here to do an example to make it the 4 steps here more clear.